gas such as air and the different gases that are really contributing to the partial pressure of air. So we talked about the fact that if we were looking at the total partial pressure of air, we would have to add the partial pressures of the individual gases that comprises air. And so in this instance, that would be nitrogen, oxygen, and other gases that contribute to the partial pressure here. And so this is the formula that we introduced in order to calculate the total partial pressure of a gas. It's the percentage of the gas that makes up that mixture multiplied by the total partial pressure of the entire mixture, okay? All right, so in the instance of air, we said it's 79% nitrogen, 21% oxygen, and some other inconsequential gases such as carbon dioxide, helium, argon. And then water, we said, was another important factor that played a role because water has a partial pressure of its own. And so looking at this example of calculating the partial pressures of nitrogen and the partial pressure of oxygen, we simply multiply the percentage of nitrogen by the total partial pressure at sea level, which is 760, and that gave us 600 for nitrogen and then 160 for oxygen. We also said that we can look at the contribution of carbon dioxide as very minimal, so about 0.03%. And so if we were to calculate the partial pressure of carbon dioxide, it would be, again, a very small amount, about 20 to 21 millimeters of mercury. Okay, so we need to take into account the water, right, the contribution or the partial pressure of water if that air is humidified, because there's now the addition of moisture. And so we have to account for the partial pressure of water, which is about 47 millimeters of mercury. So if we recalculate the partial pressures here, we'll see that nitrogen is now lower. So instead of 600, it's now 563. And for oxygen, it's going to be 149 instead of 160. And this is because if this air is not dry air, if it's humidified, all of the other partial pressures become smaller because we now account for the partial pressure of water, okay, which is 47 millimeters of mercury. Okay, so that was the first, yep.
For the last slide, we don't have to know the exact numbers of like the pH, low and PM2. Are we have to memorize?
So not memorize, but understand how we got the numbers is more important. Okay, so this equation, be familiar with this equation, okay? And these, right, the percentages of air. So 79% for nitrogen and 21% for oxygen. Okay, any other questions? Any other questions? Okay, so that was the first factor, the partial pressure that determined the diffusion of gases. The second factor that determines how well gases diffuse is the solubility of that gas in a liquid. So basically, how many of those gas particles can be converted from their vaporized state into that dissolved state in a liquid. So we know that gases can exist in their vaporized form and dissolved in a liquid. And in order to do so, that gas seeks to be at equilibrium in terms of its partial pressure. And to kind of break down what that means is that if I have a partial pressure of, let's say, oxygen in air, in order for that air, those air or gas particles to dissolve into a liquid, the partial pressures must be at equilibrium. So the partial pressure in the liquid must also be at 100 if the partial pressure in air in its vaporized state is 100. And we'll look at an illustration that kind of clears that up a little bit. So the partial pressures of the dissolved and the vaporized state should be at equilibrium in order for those gas particles to move from their liquid state into their, from their vaporized state into their liquid state. This brings us to Henry's law. Now, Henry's law states that at a certain or constant temperature, the number of molar concentration of the dissolved gas, which is another way of saying the number of gas particles that are dissolved in that solution, is directly equal to the constant K multiplied by P, which is representing the partial pressure of the gas in the atmosphere. So to simplify this relationship, to simplify this equation, we can say that the number of particles that ends up in a solution is directly proportional to the partial pressure of that gas. Or we can also say that, for example, the number of oxygen molecules that dissolves into liquid is directly proportional to the partial pressure of oxygen in air. Okay, so the relationship that we really want to identify here is that there's a directly proportional connection between the number of gas particles and the partial pressure. If we increase the number of gas particles, we increase the partial pressure, and vice versa. Okay. All right, so on that basis, we can speak about oxygen and carbon dioxide and their varying solubility. So at 100 millimeters of mercury, partial pressure in water, oxygen dissociates to 0.15 millimoles per liter, whereas carbon dioxide dissociates to 2 times that amount, so 3 millimoles per liter. And so what we can see here is that carbon dioxide is much more soluble than oxygen in water. And in our case, the specific fluid that we are interested in is blood, right? So what this really means is that carbon dioxide plays more nicely in blood. It's going to move around easily in blood. Oxygen does not. And this is something we said already when we talked about blood in chapter 15. We said that oxygen is actually not very soluble in blood. And so what mechanism did we speak about that compensates for the fact that oxygen does not move around very well in blood? Hemoglobin, right. So oxygen has its own little chauffeur, its own transport molecule, because it does not solubilize or dissolve or move around very well in blood. And so let's illustrate that a little bit more here. So in this first scenario, what we're seeing is a beaker that is presumed to be just water, so 0 oxygen to start. And then it's exposed to air, which has oxygen molecules present. And so if we allow time for this to get to equilibrium or equilibrate, the oxygen will dissolve into that water. So as I mentioned before, in order for dissolving or in order for that oxygen to dissolve into this liquid state, the partial pressures must be at equilibrium. And so at a partial pressure of oxygen in its vaporized state of 100, a partial pressure of oxygen in its liquid state also at 100, we see that the number of molecules varies very much, right? So we go from 5.2 millimoles of that gas in the air to only 0.15 millimoles of gas in the liquid. And so this is what we're trying to illustrate here. Oxygen does not dissociate very nicely in water. It's not very soluble in water. If we had a gas that would equilibrate or dissolve to 5.2 millimoles in liquid, that would be a very soluble gas, right? And that's kind of the relationship that I'm trying to make here. And we can compare that to carbon dioxide. So again, the same kind of setup. We have this scenario, a beaker exposed to carbon dioxide in the air. And if we allow that time to equilibrate, the amount of carbon dioxide that dissolves into that liquid is much more than what we saw for oxygen. So it's not fully or 100% soluble, because we don't get all of those gas particles dissolving, but we do get 2 times the amount of carbon dioxide dissolving into this liquid than we do for oxygen. Right? Any questions on that bit? And all of that was just to say that carbon dioxide is much more soluble than oxygen in blood. So our second objective here is to understand how the partial pressures exist in the alveoli and how they influence gas exchange across the alveoli and obviously across the tissues. Okay, So we know that exchange of carbon dioxide and oxygen takes place in two important areas. It's going to happen in the lungs, across the alveoli and the atmosphere. It's going to happen down at the level of the respiring tissues, where tissues are using oxygen and producing CO2 as a byproduct. And we're going to also speak about some of the determinants that influence how these partial pressures change. So when we speak about the movement of gas, the diffusion of gas, we're going to see that gases move from high pressure to low pressure. So once again, we're speaking about pressure gradients here. So we've talked about pressure gradients as they apply to the cardiovascular system, as they apply to blood moving in the vasculature. We talked about gradients as they apply to bulk flow of air into the lungs. And even on this cellular level, even on this very subcellular level, we also see gradients being the driving force of movement of gases from one place to the other. So gases diffuse down their pressure gradients. But even if we look at a mixture of gas, such as air, each of those gases will diffuse down their own partial pressure gradient as well. And we also want to point out that the other partial pressures or the other gases do not influence the movement of an individual gas. So in the mixture of air, we've got CO2, we've got nitrogen, oxygen. The movement of oxygen is only dependent on the partial pressure of oxygen alone. And that is why we can facilitate oxygen moving in one direction and CO2 moving in the opposite direction, because they're both moving along independent gradients in one direction or the other. Okay, so what we're seeing here is called the oxygen cascade. And this is looking at how the partial pressure changes for oxygen and CO2. And so we'll look at it in this way, and then we'll illustrate it in a different way where hopefully it's a little bit clearer. So we start off with a partial pressure of oxygen at 160 millimeters of mercury in the atmosphere. And then by the time we get to the alveoli, the partial pressure of oxygen has dropped significantly. It's dropped from 160 down to 100. And it stays at 100 throughout most of the systemic arteries, throughout most of the vasculature, until it gets to the level of the capillaries. So at the level of the capillaries, the partial pressure of oxygen has dropped to 40 millimeters of mercury. And so we have a gradient, right? We've got a gradient from 160 out in the atmosphere all the way down to 40 at the level of the tissues. And so this gradient is the driving force that moves oxygen into our cells and eventually even into the mitochondria, right? Where oxygen is used as that final electron acceptor. And we can look at carbon dioxide going in the reverse, right? Carbon dioxide has a partial pressure of 46 millimeters of mercury down at the level of the tissues, and then it goes to about, it stays at 46, and then it eventually drops to about 40 at the level of the alveoli, and eventually there's a significant drop off from 40 down to 0.3 back out in the atmosphere. And again, what we're seeing here is a gradient that facilitates the movement of CO2 from the tissues where that CO2 is produced as a byproduct, all the way through the vasculature, and eventually that large drop off between the alveoli and the atmosphere is facilitating the exhalation of CO2 from the lungs.